Camera's on. But let's move on for now. I'm going to do 7.2, 7.3, creeping up on the test next Thursday. I'll go ahead and write down the other sections. 8.1, 8.3, and we will do more next Tuesday. We won't meet this Thursday, but I'm hoping I can get through all that today. 7. Yeah, I'm hoping to get some of chapter 9 today too, but let's just see where we get. So sizes of atoms are really comparative sizes of atoms. Something we haven't really talked about. You can think of this as, if you have this atom, and you can think of it as just a sphere if you ignore this other atom. So the distance to the very outer edge, you can think of that as the atomic radius. And there's also something called the bonding radius, because atoms tend to get a little bit closer when they bond. So what we do is take the distance between the two nuclei, cut it exactly in half for a diatomic molecule. Say it's chlorine and chlorine, or hydrogen and hydrogen. And then we take 1/2 of that and we call that the bonding radius, which tends to be a little bit smaller than the free atom by itself. But all I really want to say about these is a general trend. Because it's a general trend, if I wanted you to know specific numbers, I'd give you the numbers, but assume you won't have this on the test. Just the idea here is, so going straight down this column, you can see that the length here in angstroms, not sure I mentioned this, but 10 to the -9 meters is nanometers. 10 to the -6 meters is micrometers. 10 to the -10 meters. Next would be 10 to the -12 on that chart. But this is angstroms. We could just call that angstroms. Chemists like that because so instead of doing 128 or 0.128, we're kind of in the whole numbers. So chemists just like angstroms, 10 to the -10. But notice these get bigger. You got 0.31, 1.28, 1.66, 2.03. Atoms, whether it's the bonding radius or just the atomic radius, they tend to get bigger as you go down a column. Kind of counterintuitively, going across, they're actually getting smaller. I mean, going across any of these columns, 1.28, 0.96, 0.84, 0.76, they're getting smaller. So you can picture it like this. If you start looking at the periodic table and you go, here's hydrogen, then you go over to helium to the right, it gets a little bit smaller. And then when you go down to the next row, it gets way bigger. And then you have lithium, beryllium, boron, carbon, nitrogen. So lithium and then beryllium's just a little bit smaller, and then boron's a little smaller, and carbon's a little smaller. You get all the way to neon, but it never gets so small as to be as small as any atoms in the row above it. So, say it like this. Lithium is larger than beryllium by a little bit. Boron is a little smaller than beryllium. Carbon is a little smaller than boron. So they get a little smaller, a little smaller, a little smaller going straight across. Kind of counterintuitive, but that's how it works. So if you were comparing, use this example. That's the trend I just described, but let me get to an example. It says boron, carbon, aluminum, and silicon. If you just started with boron and carbon, based on what I just said, which one's bigger?
Boron.
Boron is bigger, so I'll say carbon is a little smaller than boron. Definitely bigger than both of those. Was it silicon? Aluminum and silicon. So up here, now we're dropping down a row. Aluminum and silicon. These both are definitely bigger than these two. So I'll say bigger here is the two where we drop down to another row, aluminum and silicon. Aluminum and silicon, which one's bigger?
Aluminum's bigger. Silicon.
Aluminum's bigger. Yeah, so I would go silicon, aluminum. So of these four atoms, this one's the smallest, this one's the biggest, and this is the way you would rank them if you were just going to rank them. So smallest, next biggest, and then we jump way bigger, and then even bigger aluminum. Can you see that by looking at the periodic table? That's kind of all there is to say, but the reasoning here is when you go from lithium to beryllium, or let me say sodium and magnesium. So sodium has 11 protons in the nucleus, and then you have that first shell, the 1s shell, and then if you put 12 protons in the nucleus, that pulls that first shell down a little bit, which allows all the electrons to pull in a little bit. So it's that extra proton that's making things pull in a little bit more, a little bit more, a little bit more as you go across. And it's when you jump to, maybe this reminder will help, but you got your 1s, 2s, 1, 1, 3, 1, 3, 5. So hydrogen has 1 proton in the nucleus. Helium has 2, and that pulls these in a little bit, and that makes the radius a little smaller. If I go to lithium, it's like this. This pulls in even tighter to the plus 3. The negative charges pull even tighter, which allows this one to drop a little bit. And then when you get to lithium beryllium, then you have 4 protons. So that pulls this in, which allows this to drop a little more. So that's the reasoning why they get smaller when you go to the right. But they get bigger because really when I draw this, it's not really to scale. If I wanted to sort of make this to scale, I would draw the 2s way up here. Actually, these are pretty close to each other. 3p. But then when you get to the 1, 1, 3, jump way up here. So it gets smaller and smaller, but then when you get to the next level, that's 2p. It jumps way out. This electron goes way out from this one. So you jump way big when you go down to the next row. That's really all there is to this atomic size thing. You guys good with that? It's going across from left to right that's non-intuitive. And what do I have? 7.2526. Let me jump down here because these I think are very straightforward. So arrange each set of atoms in order of increasing radius. So could you do this? Ba, barium, calcium. So, I really haven't said this, but I did say it once. If you're comparing in one column, they get bigger as you go down. As you go to the right, they get smaller. What were these? So could you do 2, 5, 2, 6? So barium, calcium, sodium there's barium, there's calcium, and there's sodium. So these are going down. I know they're not in the same column, but still, sodium here would be the smallest one, calcium would be the next bigger one, and barium's way bigger than either of those. Does that make sense? I might be over-explaining it. If you're confused, it's just because I'm over-explaining it. It's really not any more complicated than that. 2.5, 2.6. So I did this one. Indium, tin, and arsenic. Where are those? There's indium, there's tin, and what was it? Keep getting lost. Yeah, arsenic. So there's arsenic, there's indium, and there's tin. So arsenic is smaller than both of these, and tin, SN, is a little bit smaller than indium. Because you get smaller as you go from left to right, but you get bigger as you go down. Does that make sense? I think if I confused you there, you're overthinking it or I'm over-explaining it, but that's what we call a periodic trend. Size trend, periodic size trend. Also put on here 28, what did I say, not A? It's because of that positive, okay. Periodic trends and ions. So this was for the neutral atoms. Let me redraw. Okay, 1s, 2s. So we'll compare a couple things here. 2p. I gotta move over. 2p, 2s, 1s. We use the phrase isoelectronic. Just a descriptive word for what I'm about to show you. Let me do, what should I do? Sodium and neon. So I'm going to need 2, no, that's good. All right, so sodium, sodium, okay. Yeah, we got to go to 3s, isoelectronic. Let me draw the 3s. Yeah, okay. Why does that confuse me? 2, 4, 6, 8, 10, 11. Okay, that's sodium. Sodium, neon, yes, neon. If I did the one for neon, so these here are the 2 level, this is the 1 level. This is the neutral atom, neutral electron configuration for sodium. But you already know this about sodium. If I said, what is the charge on sodium when it's an ion? What would you tell me? Plus 1. It gets to plus 1, so it has 11 protons in the nucleus. That is 11 positive charges. Here's 11 electrons. One of the reasons it likes to be plus 1 is it likes to lose this 1 electron, so that it has this, the valence is this full octet of an S and 3 P's full. But what you're looking at here for sodium plus now, and neutral neon, is what we call isoelectronic. Same electrons in the same orbitals. But here's the thing, neon, this has 10 protons. And this one has 11 protons, but the same number of electrons. So which one do you think pulls in the most? That is, which one do you think is smaller between these two? Which one's
Sodium?
Sodium's smaller because it has more pull in the nucleus. So when we say isoelectronic, we can compare things like neon, sodium, and what's next to sodium? Magnesium. I'm afraid I'm off camera. No, I guess I'm on camera, but I'm very small. So I'll do electronic configuration of magnesium. Okay. 135. Neutral magnesium has this going on, and it's got 12 protons. It's not that easy to compare when it's not isoelectronic, but of course, what I'm about to say is, what is the charge on magnesium when it's an ion?
Plus 2.
It's 2 plus because it likes to lose these two and get to this stable state like this. So now which one's smaller? Now that it's got 12. So this one, Mg2 plus, is smaller than Na plus, which is smaller than neon. Do you see? And it's all about those protons in the nucleus pulling them in. So these extra ones that I signed, 7.28 and 7.29. Skip this one. Iodine being positive is just weird. We haven't covered some of the more exotic things that can happen. And I think you can do the rest of these. Gallium 3 plus. So here's gallium. If it loses its 3 outer electrons, it's going to lose this one, and the calcium and the potassium. So that's gallium 3 plus. Identify the neutral atom that is isoelectronic with it. So what's isoelectronic with gallium, calcium, and potassium? Ions, but is also neutral. Gallium will lose 3 electrons, calcium will lose 2, potassium will lose 1. Here's the 3 things that are isoelectronic. Gallium 3 plus, magnesium 2 plus, oh, I was already there. Magnesium, no it wasn't. Gallium, calcium, and potassium. Calcium 2 plus, potassium would be plus, and what would I want to put here for the neutral one, if I went one more?
Arsenic?
Yes, AR, argon.
Argon.
That's what you meant though, right?
Yeah.
So argon is neutral, but these are all isoelectronic. You follow that? Now that I say it. Argon has 18 protons in the nucleus and 18 electrons. Potassium loses one of its electrons, but it has 19 protons and 18 electrons because it loses one of them to become positive. Calcium has 20 in the nucleus, 20 protons in the nucleus, but 18 electrons around it. So 18 again, 18. And gallium, once it loses its 3 outer electrons, it becomes 18 electrons again.
So all isoelectronic is the same number of electrons.
Same number of electrons. Yeah, it's fine to say it that way, but excluding excited states. So remember last time I was showing one electron pop up somewhere, as long as they're all in their ground states, the way I did it last Thursday is when I talked about excited states. So a photon comes in, pops it up to an excited state, it drops back down, a photon comes out. But excluding excited states, if you made these configurations, they look exactly the same. Electrons all in the same. That's what isoelectronic means. And yes, in the same number of electrons. So, zirconium is here. And zirconium 4 plus means you lose this electron, this one, and this one, and you're going to go back over here and go krypton. So krypton, rubidium plus 1, strontium plus 2, yttrium plus 3, and ZR plus 4 are all isoelectronic. They have the same number of electrons. But really the point here is zirconium will be the smallest one out of all of those. And the next smaller one will be yttrium, the next smaller will be strontium. I know y'all probably haven't learned all those names, but this one, this one, and this one, and this one, all the way back to krypton. This one's the smallest because those 40 protons pull it in tighter than the 39 protons there, the 38 protons there. So isoelectronic. So when we compare ions, we like to compare apples to apples. That is isoelectronic configurations is what we want to compare. 729, did I put 730? I guess I should have. Yeah. Add 730. So 729 is the one, the red one. Based on what I've said so far, isoelectronic chlorine, I haven't done one of those, going the other direction, comparing chlorine. Do I want to make that? Yeah, I guess I can. 1s, 2s, 2p, 3s, 3p, 1, 1, 3, 1, 3, 5, and really the next S, 1s, 2s, 2p, 3s, 3p, 3d. The 4s actually starts here. Chlorine. But we're really only going to go up to chlorine is that's chlorine. Chlorine, if I ask you what is the charge on chlorine, what would you tell me when it's an ion?
-1.
That means it's got an extra electron. It's going to go right there. So that's Cl negative. And 17 protons in the nucleus. Now compare that with, look at chlorine, and just to the right of it is argon. Argon has 18 protons, but that's the configuration of argon. So now we have 18 electrons up here and 18 here. But argon's going to pull those in a little more because of the 18 protons versus 17. So if you're comparing argon and chlorine, argon is smaller than chlorine because of the extra proton in the nucleus. Make sense? All right. So when we compare ions, we want to compare the isoelectronic ions, just so we're comparing apples to apples. 31. And yeah, those I say just A. Yeah, just a 31 and 32. 31 and 32, just a, and what is 33 and 34? Yeah, you can skip C here, the long-winded explanation. List the atoms in order of increasing size, list the ions in order of increasing size. So you rank these just as atoms, and then you can rank them in size as their natural ions. So I think y'all can do those. But that's, so atomic size, I could say atomic radius, and atomic radius, and ionic radius. I think that's all I want to do in 4. I mean, in chapter, what chapter is that? 7. Sizes of, I know I'm going to do ionization energy. That's 7.49 and 7.50. Let's, all right, ionization energy. These are energies in kilojoules per mole. We're talking about energies here. The easier it is to pull the first electron off of something, the lower amount of energy it takes. And then if you want to take the next electron off, it generally takes more energy. So let me, I guess I'll draw sodium again. That. 3s. Okay, so there's sodium. If I want to pull this electron off, this chart is telling you 496. If I wanted specific numbers, I would give you these on a test, but I don't think I'll give you these. It's a general trend, just like the other chart. It's a general trend to know. But what to know about this is, if I said how many valence electrons in sodium, do you remember how to do that? You look at the periodic table and you count. So how many valence electrons in sodium? Yes. So it's just 1. You look for the highest level, like this is the number 1 level, or n equals 1. This is n equals 2 level. Here we are at the n equals 3 level, and this and the 3p and the 3d all go together. There's only 1 electron in that, and then there's no more electrons. There's nothing in 4, there's nothing in 5, there's nothing going on up. So that's the valence electron, but you can get that easy from looking at the periodic table and counting to the left. So sodium has 1 valence electron, and that's telling you it takes 400 and about 500 kilojoules. You put energy in, and you can push that electron out off into space somewhere, and now you have an A plus. That takes about 500 kilojoules of energy. But look at the next energy. That's called the second ionization energy. So the symbols here are first ionization energy. That's what I've been talking about, and that's the one y'all are familiar with when I say sodium ion. But first ionization energy. If I'm going to take another electron out of here, we have that stable octet here. And the atom, the electrons want to stay like this. So pulling another electron out of here, doing that takes a lot of energy. So you see the jump in energy to pull that second electron off. So going into the what we call the core, I'll remind you of this. There's sodium before it's ionized, so that's sodium. You got your valence electrons, and then everything else down here are called core electrons. So if you have to pull out a core electron, you've got 2 things working against you. One of them is you're trying to remove a negative particle from something that's already positive. I might not have said this, something I could have said right at the beginning of the semester. 2 positive charges repel each other. They don't want to be near each other. Two negative charges, same thing. They repel each other. And a positive and a negative, though, those will be attracted to each other. That's the way I'll diagram it. Maybe y'all knew that from somewhere. But, positive and negatives are attracted, but negative repels, positive repels. So here we are trying to pull out a negative electron, but the thing is already positive. So if I had this, and I start to pull that electron out, and say it's only about here, this is only a little bit positive. But I pull it out a little more, now it's a little more positive, and eventually I get this far enough away that now it's positive. But this second electron is having to leave an atom that's already positive. So that's one of the reasons the energy goes up to get this one to remove. And the other one is that idea that those core electrons are very stable as they are. So if you have to reach into the core and pull out an electron, ionization energy goes up a lot. If we look at magnesium, so here's magnesium, neutral magnesium. And you see the first ionization energy, 738. 738, to pull that first one out and make it positive. But you already know it loses both of those to become 2+. If I asked you what's the charge on magnesium weeks ago, you would have said 2+. So it actually loses both of those. It loses one, costs that much energy to lose the other one. What does that say, 1,500 or something? And then that's where it's stable in compounds. But notice the next jump, the third ionization energy, now we have to pull a negative electron away from a 2+ charge. And on top of that, we're trying to get it out of the core. That's why this huge jump into the 7,000s. So it's about the second ionization energy is about pulling away from a already positive charge. So there is a pretty good jump to here from here. It's about double. But you jump way up when you have to reach into the core and start pulling them out. And I could go on with aluminum. Aluminum's next. Here's aluminum. And it's the same trend. There's neutral aluminum. We pull the first one out, it's positive, but you already know that's not really stable. It's going to lose this one for an even higher cost, and it's going to continue, and then we lose this one for an even higher cost. That trend, getting higher and higher and higher, that's about, this one just pulls away from the neutral atom. But as soon as that electron starts to leave, the atom starts to become positive, so there's some energy associated with it. Getting the next one out costs more, and then getting the third one out, this third electron is trying to pull away from something that's 2+. And by the time that electron's completely gone, it'll be 3+. So that's why the jump here. And then here's this huge jump to 11,000 kilojoules. That's, again, when we're trying to pull something out of the core. So you can make stable atoms and ions and compounds are what we've been talking about, but you can zap things with electricity or heat them to really high temperatures or bombard them with particles to get more electrons to pop out. So it's possible to do this, but losing one electron here, that doesn't tend to happen in chemical reactions we do. It's always going to lose 2. Aluminum will always lose 3 to make something like aluminum oxide. So your typical chemical reaction won't do all this, but it's still possible using bombarding with particles or high heat or electricity or something. So if you're wondering why I'm showing first ionization energy for magnesium when you know it loses 2, that's generally what happens in a chemist's lab. Physicists are the ones that bombard things with particles.
Why is the first ionization energy for magnesium higher than aluminum if aluminum has more protons? Is it because the electrons are further away?
Oh yeah, I do need to mention this. It's A, because they're further away. Because these are a little further away. But it's also something called shielding. If we have time, I'll go back to this concept and we'll talk more about it. But it helps conceptually to know this now. This electron, it really doesn't feel all of this because these electrons here, so you got a bunch of positive charge here, and then you got some negative charge going on here, and some more negative charge, and some negative charge, and some negative charge. This electron has to feel this positive charge through all this cloud of negative. So that's why this one would take more energy than, say, this one. And then these are actually feeling some shielding too. So shielding weakens it, but I should have said this. This attraction the closer they are, the stronger the attraction. The further away they are, the weaker the attraction. Similarly, the higher the charge at the same distance will be a stronger attraction. So this one is further away from the nucleus than these. Weaker attraction. Everything I'm telling you is counterintuitive. Oh, I see what you're saying. It goes back down for aluminum.
Yeah.
So now to tell you a trend that makes sense to what you just asked me. There is an attraction these two electrons have to each other, even though I said negative, negative will repel. I didn't say this yet. If we have time to go back for it, we'll go back to it. But electrons have, so you have your negative charges, which will make them repel, but they all also have what we call the magnetic pole. So you've heard of electromagnetic radiation, two forces that kind of work together for photons, for light. Another word for electromagnetic radiation, sometimes we just say light. But usually when we say light, we mean the visible range of the electromagnetic spectrum. I showed you that spectrum that's way wider than just visible. But just like, have you ever played with, you guys have probably played with those little neodymium magnets. I remember when I was a little kid, we had big iron magnets. But the north and south pole, I think it is, will attract to each other, but the north and north poles will repel each other. And it's the same with the neodymium magnets. You get them, two of them to click together, but you work really hard to flip one over, and then you just hold on to one, the other one will go pew across the room. So what the two electrons will do is, I think it's like that. I think north is attracted to south. So the reason these two still end up stuck to each other is because it's not just the electric force that's there. There's this magnetic force that will make them click together. So this one doesn't have an electron holding on to it. So it can get out easier than one of these. That answers
So
your
pairs
question.
are kind of hard to break apart.
Exactly. Because of that attraction, they're stuck together. So trends in ionization energies. First ionization energy, second ionization. And of course, the reason we call it ionization is because we're creating an ion in the process of removing electrons. So 7.49, 7.50. See if those are sensible. based on the position of the periodic table, let me do these. So which has the smaller first ionization energy? Titanium and barium. Okay, now it's gonna be shielding. So you've got a neutral titanium that loses 1 electron. That takes a certain amount of energy. And then you've got barium down here. So based on size trends, titanium and barium, which one's bigger?
Barium.
It's barium, and it's by a pretty good amount. So just relatively, what is it, titanium? I'll just make it this. The outer electron in barium is further away from the positive charge, so it's initially just on the face of it has a much weaker attraction to the middle of the atom, to the protons, and this one's much closer. This is a stronger attraction because they're closer. The electron out here is closer to the protons, and these are further, so weaker slash. So the electron in the barium, the first electron you want to remove from barium will be easier to remove than titanium. That makes sense, based on distance. Closer they are, the stronger the attraction, further away. So size, if you want to talk about removal of the first electron, size comes into play here. I think all these are sensible. Okay. There's silver. Silver and copper. Again, it's size. So you've got silver here, copper, right? That's what I'm doing. I want to be doing these. Silver and copper. So which one's bigger? Silver or copper? Cu is copper, Ag is silver.
Silver.
Silver's bigger, therefore it's easier to remove that outer electron because of the distance between the nucleus. GE and Cl. There's Cl and there's GE. GE is bigger than Cl. Move an electron. So same idea. Makes sense. So it's harder to remove an electron from a chlorine than it is from germanium. Lead. You got Sb there and lead there. The 4s is further out, or the 4d is further out. I better make the, well, I never did make it really big. Three, 5, and 4s. E, is that where we're going? 1, 2, 3, 4p, 5s. 1, 2, 3, 4, 5. 4d. That's the 4d. 3d. 2p. So all of these full up to SB, it's 1, 2, 3. 1, 2, 3, 4, 5. What did I do? 40. Now I have to do 5. And then SB, 3 of them. So pretend all these are full, and that's the valence. Whatever, I'll draw them in. So the valence electrons here, the highest n number, n equals 1, equals n equals 2, n equals 3 are split up a little bit, n equals 4 are here, and there's the 4d, and then n equals 5. 5 is the highest level that has electrons in it, so you count the ones in 5s, you got 1, 2, 3, 4, 5, 5 valence electrons. And we're comparing that I can't help it, I gotta fill these in. Okay, there's the electron configuration. SB, and what are we comparing that to? Lead? Is it lead? Yeah, lead. Oh, why am I doing that? It is SB and PB, right? I was looking at palladium. Lead is bigger. Lead is bigger. Well, I did a big electron configuration. I've been wanting to do one of those. But lead is bigger, so it's going to be easier to remove from lead. Do you see that? Yeah. There's lead. All right. I think you guys can do those. If any of it comes off counterintuitive, just bring it up next time. But I tend to try to avoid ridiculously huge electron configuration, but I guess that's reasonable size. Okay, that I think is all I want to do in chapter 7. All right, chapter 8, concepts in chemical bonding. I'm really going to kind of skip over ionic bonding, but let me do this as a quick review or a quick reminder. I said earlier in the semester, there's ionic compounds, there's really a fourth, so I feel like I got to put it down. And then that's a complete list of all the compounds in the universe made of atoms. That's why I like to do it. It covers the whole universe. We don't really talk about these. We kind of touch on metallic. I mean, in any of these reactions where I went, and it's just Na by itself and it's S, that's metallic, it's neutral. If I did CuS, that means copper neutral, not the ionic form. And that, I said this earlier in the semester, but you can get confused over what we talk about, metals and nonmetals. These, when you write the metals from the periodic table like this and they're neutral, you already know that. That's metal. Things that go clang, you know what metal is, a stop sign, the change in your pocket. So I like to point that out. Some metals are brittle and weird and they're not like that, but most of them are exactly what you thought of as a metal before you came to a chemistry class. This is see. The atoms are neutral here for those. I'm not really going to say anything about coordinate covalent. And then we've talked a lot about ionic compounds. This is between a metal and non-metal. And I'll say charged. Those are charged. So we talked a lot about these. Now we're finally getting covalent compounds. So only metals and non-metals, and this is only non-metals. So metals and non-metals, those come together to make the ionic compounds. The type of bond between them is an ionic bond because it's literally, say, a +2 charge attracted to a -2 charge. And that's what makes them bond, the electrostatic attraction. Metals, the bonding is, I could put metallic bonding, and that's kind of odd, and that's kind of not a 12-11, but a 12-12 type concept. But here, when we're dealing with only metals, this is what we call molecules, and we're finally there to molecules. Other books I use tend to get the molecules a little sooner, but most of the stuff around you, not counting the metals, are made up of molecules. If you're standing out in the woods, everything around you, including a few feet down below you, is all organic compounds. That is, they're all molecules. If you're out in a natural setting like that, you have to dig down a bit to get to the minerals and stuff. That's where the natural ionic compounds are. And there will tend to be metal compounds in nature. Now leave nature and come to the modern world. Still, most of the things around you are molecules. I think stuff like this, sheetrock has gypsum in it, and that's kind of an ionic compound. That and, you know, the stone block that you see in schools a lot? Okay, stone, think ionic compound, but that's it. Everything else that isn't metal are molecules. Wood, all biological things are made up of molecules. Plastics, this kind of laminate, what that's made of, what you're made of, everything else in here is molecules. So it's weird to me that we take so long to get to molecules. Anyway, so molecules, we're finally to molecules. Only nonmetals, and also notice when we start talking about these, we end up kind of forgetting most of the periodic table. It's that top right corner sort of that has all the nonmetals, but you have to include hydrogen from over there on the top left. So vast majority of the natural world is mostly carbon and hydrogen, some nitrogen, some oxygen, some of the halides mixed in, some sulfur, some phosphorus. These are a little more rare, and then that's it. That's the vast majority of the stuff around you are molecules made up of those atoms. But it's almost all carbon and hydrogen with a little oxygen and a little nitrogen. And then to a smaller extent, some phosphorus, and to that same smaller extent, some sulfur, and then a little bit of the halides. But it's mostly carbon and hydrogen. That's what we call organic compounds. You've heard the term hydrocarbon. So most of the stuff around you is hydrocarbon molecules. So we're finally to kind of the human world. Lewis structures. Back to valence electrons. And we'll touch on some of these. We ELI'd this in a 1211 class. But actually some of these, like boron and beryllium, and I think magnesium, will in weird circumstances make something like covalent bonds. So you might see those show up. Just don't get confused. We don't get into all the theories of bonding. But if I said, okay, Lewis structures of atoms. I'll say of atoms, because there are Lewis structures of molecules, and we're going to get to those. Yeah, I think we'll get to it. All right. Let me just jump over to carbon. How many valence electrons are on carbon? I'll remind you, you don't have to make the electronic configuration, but it's right there if you do. But you point at carbon and you go 1, 2, 3, 4. There's 4 in the outer shell. That's the valence electrons. You make a Lewis structure, you just go in a circle, 1, 2, 3, 4. That's the Lewis structure for carbon. Don't miss this, it's just too easy. Let's do nitrogen. How many valence electrons in nitrogen?
5.
There's 5. And I'm going to do this again. 1, 2, 3, 4. And now I start pairing them. 5. That's the Lewis structure of nitrogen. These are useful for building molecules. Oxygen, how many valence electrons?
6.
1, 2, 3, 4, 5, 6. Darken these in a little bit. Fluorine.
7.
Yep. 4, 5, 6, 7. 1, 2, 3, 4. Now I'm going to pair them 5, 6, 7. If I did chlorine, it looks just like this. If you looked at chlorine and counted it across, you count 7. So chlorine, so everything in the column has the same Lewis structure. Sulfur. And this is useful. So learn that little trick to be able to make a Lewis structure of atoms. What is it? Silicon. So anything in a column has the same Lewis structure. I'll also point out, we call these electron pairs, and we call these unpaired electrons. So we have 2 pairs of electrons and 2 unpaired electrons. And just let me point out, that's a correct way to do it. You could also do it like this. It doesn't matter where the 2 pairs are and where the 2 unpaired ones are. So what I'm saying is, when it comes to these Lewis structures, that's 100% correct, that's 100% correct, that's 100% correct. I tend to just start at the top and go around and then start pairing, so it always looks the same when I do it, but that's 100% correct, that's 100% correct. Oxygen has 2 pairs of electrons and 2 unpaired electrons. And just by extension, I'll kind of stick with these because they're sort of the canonical set. Oh, hydrogen, how many valence electrons? 1, so you just go 1 and that's it. That's the Lewis structure of hydrogen. All right. And like I said, these just sort of by extension are there, so let me stick with these as sort of the canonical set. What you can get from this, so now we're talking about molecules. You can look at, here's nitrogen, and if you want to know how many bonds nitrogen makes in a molecule, and I could say covalent bonds to be complete, but I'll tend to say bonds a lot. But I don't mean ionic bonds, I mean covalent bonds, that is molecules. This makes 3 bonds. The unpaired electrons, 1, 2, 3. Oxygen makes 2 bonds in a molecule, 1, 2, the unpaired electrons. Fluorine only makes 1. Carbon will make 4, because it has 4 unpaired electrons. Hydrogen will always only make 1 bond. So there you go. On a test, if I said, how many bonds does selenium make? Well, first you want to know the valence electrons. You skip this middle part when you do this. 1, 2, 3, 4, 5, 6. It's just like oxygen. I could just leave those where they are and go, and then you would go, oh, it makes 2 bonds. I mean, you would write down SE, and then you would go 6. 1, 2, 3, 4, 5, 6. 2 unpaired, that's where it's going to bond to another atom. You with me so far? Lewis structures of atoms. To make a molecule, carbon makes 4 bonds, so there they are. I'll put another carbon here and make its Lewis structure. So for ionic bonds, one of the atoms loses, say, 2 electrons, and the other atom say, gains those 2 electrons, thereby making it negative and the other one's positive, and that's what makes them attract. That's what makes the ionic bond. For molecules, they pair their electrons. So these want to be paired. So these 2 will click together, and it kind of has to do with that magnetic force that I was talking about before. 2 separate atoms will connect together, and we represent now those 2 separate electrons by a line. That indicates 2 electrons, one from this carbon, one from this carbon. That bond will hold them together. So now we're building a molecule. You with me? Now we're on molecules. I could do this. Hydrogen. And it's when you've taken care of all the unpaired electrons, then you have a molecule. So now I can make all these pair. There's a molecule. There's one of the possible molecules of the bajillion that are out there in the organic world. And we would write it like this if you wanted the formula C2H6. That's C2H6 diagrammed out as a molecule. So to show you the pairing, there is also such thing as C2H4. So how would I make that? Let me get rid of, let's do that. So, yeah, I'll just start over. So there's my 4 electrons around carbon, and here's the 4 hydrogens I'm going to work with. All right, so I can make a bond like that, I can make a bond like that, make a bond like that, and like that. And now I have these 2. I can actually take these and kind of slide them down here like this. That's called a double bond. You saw those when we were doing bond enthalpies. And so that's C2H4. There's also C2H2. I can steal these 2 away and just have C2H2, swing these in and do that. That's called a triple bond. There's no such thing as a quadruple bond. It's 1, 2, or 3, and there's no more, ever, anywhere for molecules. So there's 3 molecules I just showed you. So you can kind of build molecules playing sort of a game of Tinker Toys, just trying to connect things together. Y'all remember Tinker Toys, or is that too far back in the history of humankind? They were like little sticks and little things, and you could stick them together, like when you're a little kid. I grew up with those. Anybody nod? You do? You've never heard of these? They're called Tinker Toys. They're fun when you're 6 years old. There's oxygen. I can make 2 bonds with oxygen. So what do I want to do here? Well, let's just say I did a couple of hydrogens. Pair them up. And you know that is your old friend H2O. There's an H2O molecule. So you can just kind of play with them. As long as you get rid of all the unpaired electrons, you have a legit molecule that exists somewhere in the wide universe. Of course, there's a ton of this on Earth. The oxygen we breathe is O2. So there's an oxygen. There's another oxygen. I'll make that bond, but I still have these to do something with. I'll do that. So O2, 2 oxygens with a double bond. You with me? So far we're just playing Tinker Toys. So you're seeing these across here. Get that out of the way. It's kind of weird to do these because they don't really show up in molecules. So it's really pay attention to these, and then hydrogen. But like I said, these oddballs will show up in weird places in molecules. Okay, but that's what I just drew on the board. Carbon, nitrogen, oxygen, fluorine. What else could I do? F2, I guess. So if I did fluorine, I've got to do 1, 2, 3, 4. I don't know why that looks weird. Let me do, let me go back to carbon. There's carbon. Here's a couple of fluorines. Let's throw a chlorine in. And let's say hydrogen. There, now we can close this out. Chlorine has 3 pairs of electrons, 1 unpaired, so it only makes 1 bond. Hydrogen and all of these only make 1 bond, because these has 7. So one of the electrons is unpaired, so. We would call that CCl2 FH. I think the H would go first, but I'm just making stuff up now. So there's a legit molecule. That's not a natural one though. That wouldn't be made in a lab. I don't know, I guess that's good. What else would I do here? What if I did oxygen? Put me in here. Hydrogen, hydrogen. There's an oxygen. Okay. Carbon with its 4 unpaired electrons. Pair those, I'll pair those. I'll pair those 2, and I've still got these, so I can make a double bond there. So that's a real molecule. Okay, you get the idea. This is how molecules are. They have their unpaired electrons paired with an unpaired electron of another atom, and that's called the covalent bond. The octet rule, okay. So looking at these and these, and I kind of want to ignore these. They'll show up in weird places, but let's stick to the nonmetals. Oh, and we're really kind of ignoring these, but they'll show up in some compounds too, even though it's kind of strange. But like I said, this is kind of the canonical set plus hydrogen. The octet rule, okay. The octet rule just states that atoms tend to try to fill their octet, and that octet is so here, that's the electron configuration of neon. And here's that stable configuration where the S and the P are full, and there's 2, 4, 6, 8, that's the octet. So neon likes that because it's nice and stable. If this were fluorine, not neon, that would be fluorine. But if I ask you what's the charge on fluorine, you know that it likes to have that extra electron there, making it negative. So one of the reasons the ions form is to try to get this stable octet. That's ions though. This electron wants to pair with, I want to make it upside down, wants to pair, and if it can't get an electron to turn into an ion, it will settle for an electron, an unpaired electron on another atom, and then it'll form the covalent bond. So, and what did I say, fluorine? I'm going to go back to oxygen. So, something I already drew there. Let's do this one again. So in some sense, an atom is borrowing electrons from another atom so it can have that full octet. This carbon started out with 4 unpaired electrons, but it got an extra electron from all these bonds, Now it has 8. It's sort of borrowing one from this carbon, it's borrowing one here, one here, one here. Now it's got 8. The octet rule just states that atoms always try to do this. They try to get that full octet around them. This carbon has achieved the octet, this one has. Oxygen has 2. It's got a pair there and a pair there. These never bond or do anything. They're just lone pairs out to the side. But it borrowed an electron here and an electron here. Now it's got 8. 2, 4, 6, 8. So the octet rule is just saying atoms tend to try to get that octet. But exceptions to the octet rule, 2 main exceptions that we'll deal with is hydrogen, and I'm going to throw in boron.